So inference for sampling. Inference. The listener infers. Is what you're trying to get from data. So you come up with this sample. Why? Because you're trying to generalize that to the population. Remember the alliteration. Sample statistic, population parameter. And the easiest thing to think about this now is, we got two examples that are just pounding us in the head. And the example that we have with sampling would be political polling. And the example we have with experiments would be COVID vaccine. And it's just practical, it's in the moment, and you can think of these things in terms of that. So if we're sampling, a larger SRS the larger the sample, the less variability. So you're going here, page 270, and you're just going to read the bottom of 270 when they have that activity. It'll take you 30 seconds. I'm not doing the activity, so just read it. And this is a really helpful picture. So you've got these beads. You got this big jar of beads, and 30% of them are red. So you reach in that jar, and you take a sample, and you count the red beads, and your sample size is 1. How many red beads do you expect to get? That's your question. 30%. Excuse me? 3 tenths times 20? 6, thank you. You expect to get 6 red beads. If you didn't get 6 red beads, you consider yourself a failure. Yeah, because some people are going to get more than 6, some people are going to get less. It's the idea of, like, if you're playing a game with dice, okay? The expected outcome when you roll 2 dice is what? What do you expect to get when you roll 2 dice? What number comes up most often? 7. Why? Because there's 6 ways to get a 7 out of 36. So even though it's the expected outcome, 30 out of 36 times it doesn't happen. So there's 2 different ways to look at this. If you could pick 7 for the field, every other number, you should pick the field. That's what happened 30 out of 36 times. But if somebody made you pick a number, when you roll 2 dice, it would be silly not to pick 7. So that's the most likely, even though it's not only coming up 6 out of 36. Okay? So here, the expected outcome, if there's 20 beads in your sample, would be 6 red. If we did another sample, and of a size 100, like there's lots of bead rules. But if the same barrel, you put the 20 back in, take 100 out. How many do you expect to be red? Out of 100. How many do you expect to be red if the sample size is 100? The same one. Correct, thank you, 30. You'd expect to get 30 red beads. Okay? but the proportion is the same. It's 30%. But look what happens. When they did this simulation, and these are percents down here. They're not numbers, these are percent. It gets squeezed. The higher sample size gives more power to the center. There's less variability. Okay, so the point is, a higher SRS is preferable. Well, the larger SRS has less variability. Why wouldn't I always pick the biggest sample I possibly could? Because sampling is expensive. And what happens is, you're trying to minimize the bias, where the sample statistic fails to match one of the population parameters. And you're also trying to minimize your outlet expenditure. And if you could come up with a representative sample efficiently, you could generalize that to population, which is how this science works. Okay? And inference for experiments, that's just the heading of the book, statistically significant. You can quantify that. It is, as per the Supreme Court of the United States, something that, not as per them, but they agree. Something that happens less than 5% of the time by chance alone is considered statistically significant. Okay? And when they get 5%? It's arbitrary. 100 years ago, probably 110 years ago, there was a meeting of the world statisticians in Europe, and they came out of that meeting with an answer. You all thought, somebody here, let's have 3%, let's have 10%. They just came to a consensus. We'll live with 5%. The Supreme Court uses that threshold if somebody sued them under these circumstances. Somebody sued the court. The students brought before the court under these circumstances. Something that happens less than 5% of the time by chance alone. When that to occur, and you feel you've been wrong, you have to show that was going to occur less than 5% of the time by chance alone. So think about, I looked at this polling this morning, 538's polling, as the presidential election, the likelihood of running simulation has 15%, 85. Which means if the candidate right now that they're labeling as 15% were to win the election, that would not be considered statistically unlikely. Think about that. They're not, 538 is not saying so-and-so is going to win. They're saying the simulations tell us this is what happens. And if 15% of the time the red candidate wins the election, you might be surprised that that does not qualify as statistically unlikely. Okay? And then putting it all together, we're back here to this definition. You're responsible. Now, this is not negotiable. And we will call you on this now that we're in the building. These are the definitions I expect you to know. Just like I expect you to know 30% to 20. You know, there was an interview question when I was in college. And Procter & Gamble used this interview question. Procter & Gamble was a big hire, I think, to improve marketing. And they would ask you, right, who was the most influential person in your life in your teenage years? You're going, right? And then the question was, what's 30% of mine? Meaning, they wanted to see if you could think on your feet. 30% of mine is sort of 30%. 30% of mine is the question. The problem was, everybody at the attorney came back and repeated it. Procter & Gamble never said the question. Everybody at the attorney got the answer. You don't look like really smart. You heard the question before. But you had to think on your feet about this. You know, I expect you to think on your feet about this. What is the definition of R squared? Put it this way. Get used to it. R squared, you need to notice, is the proportion of change in the output that can be attributed to the change in the input. You are accountable. You are accountable for the definition of bias. Bias is the alliteration definition where the sample statistic does not map on the population parameter. It's said to be biased. The third definition so far you're accountable for is the distinction between an observation and experiment. In an observation, the treatment, the participant selects the treatment. The example we did in the book was they looked at this behavior scale for 4.5-year-olds who spent the majority of the time in child care as opposed to being raised at home because their parents were both working. They didn't take these children out of the home. Their parents already put them in child care. It was an observation. An experiment big, right? COVID vaccine. It's on this highway. Now, it was 1,000. 1,000 people have volunteered to be infected with COVID to participate in the vaccine trial. Think about that? It's kind of noble. Except this. If all 1,000 of those people are selected, they all get infected with COVID intentionally, only half of them are getting the vaccine. The other half are getting a placebo. That's the only way you can do the study. So you have to sign off on this. You have to say, I accept responsibility that anybody not get the treatment. Because in an experiment, the treatment's imposed. You can choose to participate in it, but that doesn't guarantee you're getting the actual vaccines. So that's three things right now. R squared, the definition of bias, and the distinction between observation and experiment. If I expect you're in 18 hours. I don't think this answer too much. With those three things to do at 50 yourself, you should not have to turn back. I'm not talking about 100 things. I'm talking about 3. There's only going to be 3 more altogether. We're just kind of flunked. So you're going to 2 questions. 95 and 99. So we're going to pause the recording. We're going to go over 95 and 97. So 95 talks about a telephone interview that had 1,000 participants, and 370 of them said football was their favorite sport. And then it told you what the margin of error. And you see the margin of error all the time in these political polls. Like if it said in Pennsylvania, this candidate is polling at 48%, this candidate is polling at 45%, and the margin of error is 3.5%, it's a statistical time, because they're within the margin of error. And we don't calculate the margin of error, they're pointing out, and we get to chapter 8. But here, this kind of helps with another problem. Where did we get this margin of error? 37%. Like 37% of people said football is their favorite sport. That percent said no. That was the sample size, 1,000. So think about this. That number is in the denominator. Well, first of all, it says, would you be surprised if 50% say yes? Yeah, because the margin of error is 3%. Out of the 37 takes you to 40. 50% is higher than the interval. So yes, that'd be surprised. Okay? Well, what would happen if you do that? You could select a convenience sample. You could ask people at the football game, the first football game, a high school football game. If they're going to get on a high school football game, they're more likely to say football is their favorite sport. And that was just a convenient way for you to collect data. But if you did a simple random sample of everybody equally likes the chance of being selected, you'd be more likely to the parameter. Okay? But look what happens in this algorithm. In order to make increase the margin of error, say make the sample size high. How does that work? What's in the denominator? If the denominator gets larger, the fraction gets smaller. And if you look over here at the beads, we went from a sample size of 20 to a sample size of 100. So in this margin, that's why the dots were closer together. Because the spread, you have 100 down here as opposed to having 20. And it's pulling you to the center. All right? It's a no-brainer. You want to have a higher sample size. But sometimes it's hard to get a higher sample size. And in 99, so you have this problem with your data collection. Because people are looking at this clipboard and they're inclined to say, huh, I go to the gym once a week. It looks like all these people are going 4 times a week. I feel awkward. Well, I'm going to be inclined to say a higher number. What do you got? Here's how far apart they were. Now there's a dot plot there. What does that mean? Well, when we go to this question here, for 99, there's one dot above 72 hundredths. You see it right here. So that's what happened in the one simulation. That was the difference. And then B asks, or C is, determine if the difference means from part A is statistically significant. Okay? So where were we in part A? It was 0.47 was the difference, yes? And if we count all the dots above 0.47 and to the right, because it was that or more extreme by chance alone, there's 16 dots. And that means this. It's 16 times out of 100, you got that or more extreme. 16% is not considered statistically significant. You might decide that it's unlikely, something only happens 1 out of 6 times, but it doesn't reach the threshold of being statistically significant. Okay? They did what?
I didn't do more than like 0.47.
Because that or more extreme by chance alone. Because the point is, we can't just say that, because that one outcome is, if something happens beyond that, that's the same idea. It's in the tail. We didn't draw, like if you think of the curve, it's where you want the curve and then shading outside of it. Right? That or more extreme by chance alone. So that's that for 4.3 alpha.